We're going to learn how to divide polynomials using a second technique called synthetic division. So before we get started, I want to begin by reviewing long division. One, it's important to remember how to do it, and number two, we're going to use this little problem right here to draw connections between synthetic division and long division. So what we're going to do is we're going to take the cubic polynomial x cubed minus 8x squared plus 22x minus 21. And we're going to divide that by x minus 3. So what I want you to do is I want you to work through this on your own and make sure that you remember how to do long division. So hit the pause key, work through this long division problem, and then go ahead and, kind of fast forward through the video and let's pick up from there. All right, so go ahead. All right, let's start working through. X goes into x cubed, x squared times, and then I multiply both of these terms by the x squared, so it's x cubed minus 3x squared, okay? And then we're going to subtract, and when I subtract, it's going to become minus x cubed, and a minus negative 3x squared becomes plus. So if you remember, we just change all the signs to the opposite, and then negative 8x squared plus 3x squared is going to be negative 5x squared, okay? We bring down the next term and we just keep looping through those same steps. X goes into negative 5x squared, negative 5x times, so we multiply, negative 5x times negative 3 is plus 15x, and then we subtract the terms. So it's going to become minus a negative is plus, minus 15, and we get 7x, bring down the last term, and this is our last time through. X goes into 7x plus 7 times, and then we can see that when we multiply and we subtract all the terms, we're going to get a remainder of 0. And getting a remainder of 0 means that x minus 3 is a factor of this cubic polynomial. To be a factor of something means that it divides into it. All right, so here is the quotient, x squared minus 5x plus 7. Now, what we're going to do is, let's start with example 1, and we are going to divide these same polynomials using synthetic division. And I'm going to leave this long division problem in the frame so that we can make comparisons and connections between the two. All right, so this was the cubic polynomial, and we are dividing by x minus 3, okay? So the first thing we got to do is we have to set up this problem. And the setup is going to be completely different than anything you've seen before, okay? So you're probably going to spend much of the first example kind of looking at the screen going, what are we doing? But it'll make sense once you kind of get in the groove of how to divide this. So what we're going to do is we're going to line up the coefficients. And so I'm going to kind of label this. And as you get better at this, you're not going to need to do this part I'm doing in red. But we're going to write the coefficient for the x cubed term, for the x squared term, the x term, and then the constant term, okay? And so what's convenient about synthetic division is we take the variables out and we only use the coefficients. And so the coefficient of x cubed is 1, the coefficient of x squared is negative 8, 22, and negative 21 is the constant term. All right, so we just use the coefficients. So it's kind of like coming up here, but only using the terms in front of the variables, okay? All right, next thing we're going to do is we are going to put this little box right here, and this is where we're going to put the divisor. So it's kind of like over here, kind of put this part in its own little section. And what's a little different is we're going to take the divisor, which is x minus 3, and we're going to think about solving for x. So if we take x minus 3 and set it equal to 0, then that would mean that x equals 3. So what we're going to do is we're going to put a 3 in the box. And then we're going to leave a little bit of a space and we're going to put a line going across. So if you need to hit the pause key at this point just to get everything set up, then go ahead and do that. And when you're ready, let's go ahead and work through the steps of this division. Okay, so what we always start by doing is we always start by bringing down this first coefficient, okay? Now, let's start the math. We're going to multiply the 1 by the number in the box 3, and we're going to put it right here. Okay, and then we're going to add down and get negative 8 plus 3 is 5. And we're going to continue this pattern of multiplying the number underneath the line here, okay, the result 5, by the number in the box 15. Oh, I'm sorry, what did I miss? Negative 8 plus 3 is negative 5. There we go. And then negative 3 times 5 is going to make negative 15. And 22 plus negative 15 is going to make 7. So let's just stop for just a minute and see if we can look at the quotient of this and see if we can find connections. Well, what I'm noticing here is what we're getting are the coefficients, right, of the answer right here. See, there's the negative 5 and there's the 7, which is interesting. So we're actually, what we're doing is getting the coefficients of the quotient. And so if we keep going, 7 times 3 is 21, and we add it, we then get this remainder of 0, okay, which is important to know that that remainder is always going to be in this last spot. And you can see parts of the, the same steps in the long division in our synthetic division. For instance, this part where we took 22 and negative 15, well, that happened right here, okay? So you can see the connections to this. Well, the next thing we need to do is we need to then put the variables back in. And so what I want you to understand about division is that when we divide, okay, when we start by taking an x cubed polynomial and you divide it by an x to the first polynomial, what we're doing is the exponent rule is we subtract the exponents. And so the result is going to be x squared. So if you're going to start with x cubed and divide by an x to the first power, then the result is going to go down a degree. And so this is the x squared term, this is the x term, this is the constant term, and this is the remainder. And so what we need to do is let's take these coefficients and let's write the quotient. It's going to be x squared minus 5x plus 7. All right, well, the next thing that comes up is clearly this is a much easier process for dividing, so why would we even learn long division in the first place? And that is a great question. Well, the answer to that is that long division always works. Synthetic division we're going to sometimes use, okay? So when can we, let me reword that. When will we use synthetic division? Okay, well, it all depends on what we're dividing by, okay? It all depends on the divisor. So I'm going to throw in some problems, and we're going to kind of figure out when we're going to use long division and when we're going to use synthetic division, because the next piece is we need to be able to choose when we're going to use each one. Well, if I'm going to divide by the divisor, x, what did we use here? X minus 3, well, that's a synthetic division problem. If I'm going to divide by x squared minus 3, okay, then I'm going to stick to long division. If I'm going to divide by the divisor x plus 5, then this makes a really nice, easy synthetic division problem. But if I'm going to divide by 3x plus 5, I'm going to stick to long division. All right, let's do one more and see if you can draw any conclusions here about when we're using synthetic division. When I divide by x minus 2, great synthetic division problem. But if I'm going to divide by x squared plus x minus 2, I'm going to stick to long division. And so what we see about our synthetic division is we're going to use synthetic division when the divisor is in the form of x plus or minus some number. So we want the divisor to be a binomial, and we want the divisor to have a coefficient of 1, and the divisor is going to have a degree of 1. So we're going to divide by a linear binomial with a coefficient of 1. It's not that you can't use synthetic division for these long division problems over here. It's just that it requires extra bells and whistles, and the long division will actually end up being easier. Okay, so that's the when to use it. Let's go ahead and take a look at another example. Example 2. All right, so let's divide x to the 4th minus x cubed minus 8x plus 13, and let's set it up this time like this. Okay, so this is our division problem. So because we're dividing by x minus 1, we can therefore set up a synthetic division problem. So what we want to do is we want to start with our biggest degree, right, x to the 4th, and we need to fill in all the coefficients down to the constant term, okay? And so let's go ahead and fill these in. This is 1x to the 4th, negative 1x to the 3rd, negative 8x squared. Oops, something's not right, is it? Okay, let's take a look at this. Now, what's happening right here is they skipped the x squared term. And so this can be represented as having a 0x squared, okay? Then I notice that everything lines up and I can say negative 8 is the x and 13 is the constant. And that's going to be one of the most important things when we're doing synthetic division, is you want to make sure that if you're missing a term, that you fill that in with a 0, or it's not going to work out right. Okay, so in the box, if we divide by x minus 1, then that means we're going to put positive 1 in the box because we're going to say that basically x equals 1. All right, let's go through and let's divide. You can also hit the pause key if you want and see if you can get through this division on your own. All right, 1 times, always bring down your leading coefficient. 1 times 1 is 1. Negative 1 plus 1 is 0. 0 times 1 is 0. 0 plus 0 is 0. Let's keep going. 0 times 1 is 0, but then be careful. This is negative 8 plus 0, so we bring down negative 8. And now negative 8 plus 1 is negative 8, and this time we see that we do in fact have a remainder. Okay, so let's go and let's put our variables back in. So we started with x to the 4th power, and we're dividing by x to the 1st power. You will only use synthetic division when you're dividing by x to the 1st power, which means every time you divide, you're going to essentially go down 1 degree. So this is the x cubed term, this is the x squared term, this is the x term, this is the constant, and this is the remainder. And if you ever feel like you're doing the division and you skip from like x to the remainder, it's probably because you forgot the 0 for one of the coefficients. So the quotient is x cubed, no x squared, no x, and we'll just skip right to the minus 8. And then remember how we write the divisor is we express it as the divisor, the remainder over the divisor. And this is how you would then write the quotient, okay? X minus 1 goes into this quartic polynomial, x cubed minus 8 times, but then you would have to add that remainder in. Okay, so let's take a look. Let's kind of move on to the next topic. The last thing that I want to talk about is what's called the remainder theorem. And this draws an important connection that we are going to use when we start solving polynomials. Okay, so here's what the remainder theorem says. If a polynomial f of x is divided by x minus a, okay? It could be x plus a, it could be x minus a. It's basically saying that it's being divided by a binomial that's in the form of something that we can use synthetic division for, okay? By x minus a, the remainder of that division problem is f of a. So what is that telling us? Okay, well, what that's telling us is the remainder of this division problem is the same number as if we were to input the a and plug it into the function for all of the x's. So what I want to do to kind of illustrate this theorem, okay, not exactly prove it, but I want to illustrate it, is let's kind of pick out this polynomial, right? I'm just going to pick out this polynomial. Suppose we have f of x equals x squared minus 3x plus 2. And then we've got this little binomial x minus, or let's do x minus 4. Okay, let's go x minus 4, just so that it matches here what this theorem is saying. And so what we can do is we can use division And so let's go ahead and divide this, and let's put our coefficients, 1, -3, 2, and in the box we're going to put 4. And let's run through and see what this remainder is going to be. So it's going to be 1 times 4 is 4, we get 1, 4 times 1 is 4, and we get 6 for our remainder. You know, I'm going to do this right down here actually. And so the result is a remainder of 6. And what this theorem is saying is that we could then evaluate f of 4, right? We can take this number right here, what's in the box, this a value, if you will, and we can plug that a value into the function. So what is that going to look like? Well, the function again is f of x equals x squared minus 3x plus 2. Well, if we find f of, well, let me go back to this step. If we then do f of 4, then that's going to equal, we're going to plug 4 in for all of these x's, squared minus 3 times 4 plus 2. All right, let's see if we can evaluate this real quick here without a calculator. It's going to be 16 minus 12 plus 2. Well, 16 minus 12 is 4 plus 2. Isn't that interesting? Look at that. That 4 plus 2 was the same 4 plus 2 is right there, and the result is 6. So that's what the remainder theorem says. And we'll talk more as we go about the implications of this and how important that is. In fact, I'm going to do an example right now to kind of show one way that this can be useful. But that's what that is saying, is that the remainder is the same as if you plug that number into the function for the x's. All right, so let's end with an example that maybe we can use the remainder theorem, okay? Example 3. Find k so that 2x cubed plus 7x squared plus kx minus 2 is divisible by x plus 2. And another way that you might see this worded, sorry, let me scooch down, by x plus 2, is you could also see this worded as find k so that x plus 2 is a factor of 2x cubed plus 7x squared plus kx minus 2. So to be a factor of something means that it is divisible. So one way that we can do this is we could set up synthetic division, and we could say 2, 7, so this is the x cubed term, this is the x squared term, the x coefficient is k, and the constant is going to be -2. Okay, and then in the box right here, if we're dividing by x plus 2, then we're going to put -2 in the box. And we can go through and do the synthetic division even with having the k. So let's see what this is going to look like. 2, and then we're going to get -4, -7 plus 4 is 3, 3 times -2 is -6. So then be careful when you add, it's going to be k minus 6, not -6k. And when we multiply, k times -2 is -2k, and -6 times -2 is plus 12. And then let's add right here, and we're going to get -2k, and -2 plus 12 is 10. And so this right here is the remainder, and if x plus 2 is a factor or it's divisible, then that means that -2k plus 10 needs to equal 0. All right, I'm going to kind of put this right here. I'm going to make a note. It means that the remainder, which is expressed by -2k plus 10, needs to equal 0. So then when I solve this little equation, we get -2k equals -10, divide both sides by -2, and the k value therefore has to equal 5. Now, the other thing that we could do is we could use this remainder theorem, and I could evaluate the polynomial, okay? This means that I could plug in x equals -2, and the result will be the remainder, which is 0. So what does that look like? Well, that means that we could do 2 and plug in, again, what we're talking about here is we're plugging in x equals -2. So it's going to be 2 times -2 cubed plus 7 times negative 2 squared plus k times negative 2 minus 2, and set that equal to the remainder, which needs to be 0. So let's see what would happen if we solve this. Well, 2 times negative 2 cubed is negative 8. 7 times negative 2 squared is going to be 7 times 4. This is going to be a minus 2k minus 2 equals 0. So let's keep going. Negative 16 plus 28 minus 2k minus 2. All right, so what I want to do in this step right here is we need to take all these constants. And I'm grabbing my calculator right now. Let's take negative 16 plus 28 and then minus 2. And all of this is going to combine to be 10 minus 2k, or you know what I'm even going to do? I'm going to write this as negative 2k plus 10, and that equals 0. And so I think what's really interesting too is what we just did is this equation is the same as this equation right here, which is kind of interesting that these are the same. And that's another way to kind of prove this remainder theorem. So regardless, let's go ahead and solve. We get negative 2k equals negative 10, and then k equals 5. Okay? So I think, well, you know what, I know this is getting a little bit long, but I think since you are probably watching these because you were absent, I think it's important we end with this last example, okay? Little quick example. Last one I'm going to do is x minus 1 a factor of x to the 51st power plus x to the 36th power minus x plus 1. All right, so I like this last example because I think this does a good job too of explaining why this remainder theorem is important. Is this x minus 1 a factor? Well, obviously the first thing we could do is we could use synthetic division, right? And we could fill in all the missing zeros until, okay, obviously we're not going to be using synthetic division. So in this case, I don't want to think of it as having two options because we're not going to divide this x minus 1 divided by that just to see if there's a remainder. But what we can do is we can plug in x equals 1, okay? And I can plug x equals 1 in for all of these x's because what you need to understand is I don't necessarily care about all of the other parts in the division. All I care about is what the remainder is. And that's what the result will be, is it'll equal the remainder. And so if I get a remainder of 0, then that tells me that yes, it is a factor. Well, 1 to the 51st power is 1. 1 to the 36th is 1, minus 1 plus 1. And so this is going to be, let's see here, let's add up all our 1s. We basically have 1 plus 1 plus 1, which is going to be 3 minus 1. The result is 2. Well, if you're going to divide and get a remainder of 2, then that means it's not a factor. And that's what we're going to use this for down the road, is we're going to be solving, and what we need to know is what we're dividing by a factor, yes or no? And we can quickly do that by just plugging it in and seeing what the remainder is. Okay, so now we're good. That is all of the examples. I hope this made sense for today.